Dear students, let's learn more about the concept electric potential. Points of zero potential between two unlike charges. If I consider one charge plus Q1, and if I take one more charge minus Q2, unlike charges separated by a certain distance r. Net potential at any point, whether it's in between the two charges or anywhere outside, can be measured using V is equal to 1 by 4 pi epsilon naught into Q1 by R1 plus Q2 by R2. But what we find here is, since one of the charges is positive and the other charge is negative, this ratio, when it is equal to this ratio, because of the minus sign, they get cancel each other, so that V becomes a 0. So that is the meaning of points of zero potential between two unlike charges. So between these two charges, there will be a point where the net potential is 0. Not only here in between, but even outside, there will be a point where potential becomes a 0. So this topic is all about finding points of zero potential between two unlike charges. And there are two such points that exist. One, in between the two charges, nearer to the weaker charge. Weaker means lesser in magnitude. If I take plus 2 coulomb minus 4 coulomb, magnitude, that means we have to consider only the number. We don't consider the sign. Then this is a weaker charge, because it's a lesser in magnitude. Okay, so while comparing the magnitude, we don't consider the sign, only the number which we need to take. So this is a weaker charge. So such points will lie always nearer weaker charge. The second one, outside the line joining the two charges, and again nearer to the weaker charge. So there will be two such points exist between two unlike charges. The first point between the two charges, nearer to the weaker charge, and the other is outside the line joining the two charges and nearer to the weaker charge. And they have asked numericals based on that, so let's solve them. So this question has appeared again twice in the examination, and I'm going to discuss two cases. One, when the point is between the two charges, and the other when the point lies outside the two charges. Okay, let's go through the statement. Two charges, 30 nanocoulomb and minus 20 nanocoulomb, are located 15 centimeter apart. So what I am discussing right now is the first case, the first where the point lies in between the two charges. Okay, so the first charge is a 30 nanocoulomb. So Q1 is a 30 nanocoulomb and separated by a distance of 15 centimeter. Okay, let me write that in meter, which is a 0.15 meter. The other charge Q2 is a minus 20 nanocoulomb. At what points on the line joining the two charges, the electric potential is 0. So first, out of 30 and this minus 20, this is the weaker. So therefore the point will lie somewhere here, and I'm going to consider that point to be equal to P, and let that be at a distance x from 30 nanocoulomb, and the remaining distance is a 0.15 minus x. So let me write, let P be a point at a distance x from 30 nanocoulomb, where net potential is 0. So let's use the formula. V is equal to 1 by 4 pi epsilon naught into Q1 by R1 plus Q2 by R2. So this V is 0. This is 9 in 10 to the power 9. The first charge is a 30 nanocoulomb divided by the distance is x minus 20 nanocoulomb divided by remaining distance 0.15 minus x. So when this is equated to 0, so this term has to be 0. So we can write 13 to 10 to the power minus 9 by x is equal to 20 in 10 to the power minus 9 by 0.15 minus x. So this is equated to 0, correct? This is equal to 0, and when it is equated to 0, we can write this term on the other side. So now 0 will get cancelled, this power will get cancelled, and now cross multiply. 0.15 into 3 is 0.45 minus 3x is equal to 2x. So 5x is equal to 0.45, or x is equal to 0.09 meter. But this is one of the possibility that I have explained. What is the second possibility? The second possibility is case number 2. Second case, when the same charges Q1 30 nanocoulomb and Q2 is minus 20 nanocoulomb separated by 0.15 meter. And now the point lies outside the line joining the two charges and nearer weaker charge. Weaker charge is this one. So point P at a distance x. So now I will write, let P be a point of zero potential at a distance x from 20 nanocoulomb. Okay, you can even take the distance x from here also, but in my diagram I have taken from 20 nanocoulomb. So net potential formula, V is equal to 1 by 4 pi epsilon naught Q1 by R1 plus Q2 by R2. So this V is 0, 9 in 10 to the power 9. The first charge is 30 nanocoulomb divided by, to the point, to this point, it's 0.15 plus x minus 20 in 10 to the power minus 9 divided by x. The distance is nothing but from the charge to the point. So when equated, so this term should be 0. So 13 10 to the power minus 9 by 0.15 plus x is equal to 20 into 10 to the power minus 9 divided by x. 0 will get cancelled. So 3x, here 3 into x is equal to 0.15 plus x, or 2x is equal to 0.15, or x is equal to 0.075 meter. So this is the way we can find the points of zero potential between two unlike charges. So important numerical, the question has appeared twice in the examination. Okay. So let's learn more about the electric potential. Electric potential due to charged spherical shell. So if I consider a charged sphere, uniformly charged spherical shell having radius capital R, Q is the total charge on the sphere. Then what is the potential, well, outside here, V out, at a distance small r from the center of the sphere? The formula is V outside is equal to 1 by 4 pi epsilon naught Q by R is the formula. That is at a point outside. At a point on the surface as well as at a point inside, V inside. So, at a point on the surface and inside, the potential is same, they are equal, and that formula is given by 1 by 4 pi epsilon naught Q by capital R, where capital R is the radius. See, when the point is well outside, it is Q by small r. When the point is shifted on the surface, the format becomes a Q by R. So, what is the electric potential at a point well outside? V is equal to 1 by 4 pi epsilon naught Q by small letter r, where r is the distance of the point from the center. Whereas, potential on the surface as well as inside is given by V is equal to 1 by 4 pi epsilon naught Q by capital R. Okay, is the formula. So, this is regarding the electric potential due to charged spherical shell, and we have a numerical based on that. So, let us see how to solve this particular question. So, statement goes like this: a hollow spherical conductor of radius 0.2 meter. So, radius is given capital R, 0.2 meter, radius is given, has a charge of 4 nanocoulomb, Find the potential due to this charged sphere on its surface. So, we have to find the potential on the surface. So, potential on the surface is 1 by 4 pi epsilon naught Q by capital R. 1 by 4 pi epsilon naught is 9 into 10 to the power 9, and the charge is a 4 nanocoulomb divided by the radius, which is 0.2. So, this will get cancelled. 9 4s are 36 by 0.2, which is same as 360 by 2. So, the value is 180 volt. Next, V inside the surface. So, V inside is same as that on the V surface, right? So, that is equal to 180 volt. It is one and the same, and at a distance of 0.25 meter outside from its surface. So, what is the value of R? R is always measured from the center of the sphere, but here they have given 0.25 meter outside from its surface. So, we have to add the radius and then 0.25. The value of the radius is a 0.2 plus 0.25, which is 0.45 meter. So, now we can calculate the potential outside. So, V outside is equal to 1 by 4 pi epsilon naught Q by small letter r. That is 9 into 10 to the power 9. The charge is 4 nanocoulomb, 4 nano divided by R, which is 0.45. So, this power will get cancelled here. This 9 by 4.5 is 2. So, therefore, 9 by 0.45 is nothing but 20. 20 into 4 here, which is 80 volt is the answer. So, hope you have again understood the numericals and all the formulas based on which these problems can be solved. So, let us learn again some more concept, and what is an equipotential surface? Give an example. So, this again an important question. So, what is equipotential surface? A surface over which the potential remains the same is called equipotential surface. For example, if I consider a charged sphere, not only a charged sphere, but a charged conductor of any shape, So, in this case, the potential on the surface is same at each and every point. It is the same at each and every point. Even here also it is the same at each and every point. Okay. And such surface where the potential is the same potential is equal is called equipotential surface. So, a charged sphere or a charged conductor of any shape is an example for equipotential surface. So, what is the definition of equipotential surface? The surface over which the electric potential is same at all the points is called as an equipotential surface. So, example, the surface of a charged spherical conductor is an example, one example. So, one more example, the concentric spherical surfaces which encloses a charge, point charge at the center. So, if there is a charge here, any charge, okay, positive or negative, then concentric spheres are another example for the equipotential surface. Okay. So, surface over which the potential is same at each and every point is called as equipotential surface. So, charged spherical conductor or conductor of any shape is an example for equipotential surface, and one more example is concentric sphere with the charge at its center is also another example for equipotential surface. So, what are the properties of these equipotential surface? There are three properties. So, the first property, on equipotential surface, the work done in moving a charge from one point to another point is 0. Suppose if this is the equipotential surface, since the potential here and here is same, what is the potential difference? So, potential difference, okay, is a 0. So, work done is always the charge moved into the potential difference. So, since the potential difference is 0, the work done in moving any charge on an equipotential surface is always 0. The second property, an electric line of force is always perpendicular to an equipotential surface. So, suppose if this is the equipotential surface, then electric lines of force, they are always normal or perpendicular to the equipotential surface. If this is the equipotential surface, then the lines of force, they are always normal. So, the angle between the equipotential surface and the electric lines of force is always 90 degrees. So, that is the second property. And the third one, no two equipotential surfaces intersect each other. So, if this is one equipotential surface, there is no overlapping of two equipotential surfaces. They do not intersect each other. So, this is another property of equipotential surface. So, the three properties are: on an equipotential surface, the work done in moving a charge from one point to another point is 0. An electric line of force is always perpendicular to an equipotential surface, and no two equipotential surfaces intersect each other. So, hope you have understood regarding the important concept called equipotential surface.